Hello, everyone. Okay, so today we're going to talk about mechanisms again. Now, we still haven't published it. However, we are giving you an extra week to finish it. Okay, so the deadline will be moved to the 19th of May. So you have some time to go over it. Now, yeah. So apologies for that. Just taking us a long time to make it perfect. So yes, so we'll get there. The deadline for physics will be the 19th of May. Okay. Right. Okay. So let's go to do some more physics today. So today is physics, machines part 2, and we started with hydrostatics. It's an interesting topic, not studied too much in school. So problem 1, we have 2 pistons, and from the picture you can immediately tell which piston is heavier, because if they were well, actually no, that's not true. Even if the pistons were the same mass, could be still a difference in height. But anyways, M1 is 1 kilogram, and this is 2 kilograms. And we have the diameter. Diameter is 6 centimeters. And we have 3 centimeters. The liquid is water. Well, if the liquid is water, we know the density. Density is 1,000 kilograms per cubic meter. Okay, so how many assignments? We have this is assignment 8. This will be due, so maths is due on the 12th of May, and physics is on the 19th of May. Assignment 09 will be due approximately 10th of June. And assignment 10 will be due about the 7th of July. And that's it. So the final assignment is July. Okay, so 3 more assignments. Assignment. Okay. Find the height h. So you need to find the height, the difference in height. Okay. So to find the difference in height, well, what do we do? Well, let's see what we're dealing with. So liquids work in a way that the pressure in a liquid is the same throughout, well, same in all directions. It only changes with the depth. Basically, what that means that if we are sitting here or we are sitting here, the pressure is the same. So if we take P1 and P2, P1 is the same as P2. Does that make sense? Or would you like a more in-depth explanation of that? Actually, you know what? I can demonstrate that. So fit hydrostatics, statics, under pressure. Yeah, that's it. So if we take a grid and we put a pressure meter, we put a pressure meter here, and we put a pressure meter here. At the same depth, the pressure is the same. At a different depth, the pressure is higher. Okay, but at the same level, the pressure is always the same. Now, if I add a mass here, you can see the pressure increases, but in both cases, the pressure is the same. It doesn't matter if I move it right here underneath, the pressure is going to be the same. Okay. If I add another mass, the pressure increases, but it is always this. At the same depth, the pressure will always be the same. That's how liquids work. Now, so at P1, pressure at P1 and pressure at P2 is the same. So what produces that pressure? So above P2, the only thing that is producing the pressure is that piston. So we can say that P2 is equal to the force, which is mg. So let's call it M2G, multiplied by the area. Divided by the area, divided by A2. And for this piston, the pressure P1 for this piston, the pressure P1 is equal to the pressure produced by the piston, which is M1G over A1, plus the extra pressure from the depth, plus rho GH. Okay. And from here, I can work out the pressures, right? I can. So M2G, so M2 is 2, G is 10, and divided by A2. A2 is the area of this, so it's pi r squared, which is 2 times 10 divided by pi multiplied by r, which is 3 centimeters. 3 centimeters is the diameter, so it's 1.5. But it's centimeters, and we need meters. So it's 0.015 squared. And that gives us 20 divided by pi divided by 0.15 squared. 28 kilopascals. 28,000 pascals. Now P1. So P1 is equal to 1 multiplied by 10 divided by A1, which is pi multiplied by 0.03 squared, plus rho, which is 1,000. That's the specific gravity, specific. That's the density of water multiplied by 10 and multiplied by H. So that's equal to 10 by 0.03, 3,536, 300 plus 10,000 H. And we know that pressure 1 is equal to pressure 2. So now we can equate them. All right. So 3,536 plus 10,000 H has to equal 28,000 pascals. And from here, H is 28,000 minus 3,536 divided by 10,000. So 28,000 minus 3 minus answer divided by 10,000, and that is 2.44 meters. Okay, it's slightly unrealistic considering the picture we've drawn, but it's water. If it was mercury, it would be different, right? If the liquid was mercury, that's why mercury is used in barometers or sometimes in manometers. 2.44 meters. Okay, that's I hope. How well do you understand this question on a scale of 0 to 10? Just 2 people? What about the rest of you? Vishaka, Ikshita, Anne, what do you think? Please ask. I'm happy to explain. So can you ask which part is confusing? You see the problems. Well, bottom line is, if you have a cylinder with a liquid and you have a piston on top, and this is liquid, the pressure at the bottom, is going to be the pressure of the liquid is rho GH plus the pressure from this mass. And the pressure from this mass is the weight divided by the area. So if you have 2 of them, and one piston is here, and one piston is here, so the pressure at the bottom has to be the same because this is pushing and this is pushing. But so pressure 2 is just the weight 2 divided by A2. So the weight of that piston divided by the area. And here we have weight 1. So pressure 1 is weight 1 over A1 plus the extra pressure from the liquid plus rho GH. And once you have this and you make it equal to that, that's it. That's how you solve. And then and everything else is just maths. Okay. That's good. All right. Okay, enough with hydrostatics. Let's go to statics. Okay. This looks very complicated. AC is a uniform rod of mass M1. What is the minimum mass M2 in order for the string BC to be horizontal and rod AC to be at an angle alpha to the vertical? Is the equilibrium stable? Okay. So the question is, well, you can imagine a rod. If you add a mass here, this will pull the rope and hopefully the rod will stay in this position. If you add more mass, the rod would move higher. If you reduce the mass, the rod will move lower, right? So it's like on a pivot. So we have a rod. Can't see myself. Not that I really want to, but you have a rod and a rope pulling like this. So A is fixed. Okay. Yeah, everyone's on board with the question? Oh, that's a very good question. So yeah, there is, but it's a very small one. We assume that this is very small. That's why I said when we did. So the question is, why is there no rho GH on this one? Because the amount of liquid below the piston is small. And here I said we're taking the pressure at this point and pressure at this point. So we're completely ignoring the liquid below. So we're taking the pressure at these 2 points, and above this piston, there's no liquid. Does that make sense? Okay. Now, what we need to do in these questions, you always take the rod. Takes the rod. The only thing that it is moving is the rod. And look at the forces acting on that rod. So you take the rod, maybe separately, and the forces acting on the rod. So there's an M1G force, M1G force, and there's the rope. There's the tension on the rope, T. Tension. There is some kind of force here, which we don't really know. I assume it is somewhat this way. We don't know that force. That would be the reaction force. But the beautiful thing about this system is that we can apply the principle of moments. Take the moments about that's point A. Taking moments, what are the moments about point A? Okay. So the moment let's call this D1. And let's call this D. Okay, let's not call this anything yet. So the clockwise moment, because M1G produces a clockwise, it's attempting to rotate it clockwise. It's attempting to rotate it clockwise like this. And the moment is the force times the distance. In our case, the force is M1G, and the distance is the distance from the pivot to the line of force. So it's the distance from the pivot to the line of the force. Not this distance. We don't need this distance. No, we're taking this distance. It's the shortest distance from the pivot to the line where the force acts. So it's D1. And we can see that D1, if this side is L over 2, because the length of the rod is L, then D1 is L over 2. Do we have an angle? We do have an angle. L over 2 multiplied by sine alpha. Okay. So that's equal to m1g multiplied by L over 2 sine alpha. Now, which force produces an anticlockwise moment around the pivot? Which force produces an anticlockwise moment around the pivot? T, yes. There's only two forces. So the M1G, this force, is attempting to rotate it clockwise, that way. And this force is attempting it to rotate it anticlockwise. So it's equal to T multiplied by to the distance from the pivot to the line of force. So D2. T multiplied by D2, which is T multiplied by D2. So D2 is going to be L multiplied by cos alpha, right? Because this is alpha from the right angle. This is L. We get L cos alpha. L cos alpha. Now, interestingly, if you look at this mass, the tension has to be the same as M2G. Tension is M2G because that's the only force that is producing the tension. And that means that this is equal to M2G L cos alpha. Now, in order for the system to be in equilibrium, the clockwise moment has to equal to the anticlockwise moment. And that means that M1G multiplied by L over 2 sine alpha has to equal to M2G L cos alpha. G cancels, L cancels, dividing by cos alpha, divided by cos alpha, we get sine alpha over cos alpha equal M2. Now multiply by 2 and divide by M1, and that means that tan alpha is equal to 2M2 over M1, and oh, we're looking for M2. All right, apologies. That's not what I got carried away. So okay, so M2 is M1 divided by 2. So M2 is, so the answer, M2 is M1 over 2 tan alpha. Okay. Is the equilibrium stable? It's a difficult question to answer. Let's come back to this if we have time. Okay, it's not it's a little bit outside what we're trying to achieve. Basically, the question when they ask if the equilibrium is stable, the question is what would happen if this rod were shifted, let's say like this? What would happen if the rod went like this? would it return to the original position, or would it keep going? I think it would return. And yes, it is stable equilibrium. It will return. I can say for sure. Yes. But it will take it's quite an advanced thing to prove. So I don't think I would want to spend time on that at the moment. I mean, it's fascinating, but let's keep it simple for today. Have a think about it. Like if it shifts randomly, yeah, if you push it out of balance, will it return or not? If it returns, it's called stable equilibrium. If it doesn't return, it's called unstable equilibrium, right? So like, imagine you are in a bowl, and a ball in a bowl is stable, because if you move it sideways, it will return. If you have an upside down bowl, and the ball, this is unstable. It can balance on the top, but it won't remain. If you shift it slightly, it won't come back. And if it's like this is called neutral equilibrium. Types of equilibrium. Okay, moving on. 2 playing cards. If you ever built anything with playing cards, you know that it's a hassle. 2 playing cards placed like this scenario. What's the minimum friction coefficient so they do not slip? It's an interesting one. Like, there has to be friction with the floor, right? Because if there's no friction with the floor, they would go like this. And you might have experienced this if you ever played with cards. So friction is the thing that keeps them together. But why? Why do you need friction to hold them? What pushes them apart? What force pushes them apart? Friction keeps them together. No, well done, Luke. Yes, excellent. The normal reaction force. That is the force between them. So right here, we have a normal reaction force because they're pushing against each other. They're pushing against each other, so they are pushing themselves apart. Well, we'll only draw one card. So forget about the existence of this card. We're only interested in this one. So there's a normal reaction here. Let's call it R1. There's a normal reaction here. Let's call it R2. And there's a friction force. There's a friction force here. F2, F, just F. And there's a gravitational force here. mg. Okay. That's it. That's the 4 forces. Now we can see immediately that this force has to be balanced with this force. So we can say R1 has to equal to F. And also mg has to equal to R2. Well, you need to understand, you need to think of which way is the card trying to move. The card is trying to move to the right. That means that the friction force has to be to the left. The friction force will always oppose the way you're trying to move. The friction force won't prevent you from slipping. So imagine for a second that the friction force was that way. The friction force would be helping R1 to push the card sideways. There's no other forces. So the horizontal forces would be unbalanced. That's how you know. Horizontal forces have to be balanced. All right. Well, we also know that if there's a minimum friction coefficient, that means it is at the point of slipping. That means that the friction force is equal to mu multiplied by R2. So we can write that R1 is equal to mu R2. Okay. So we have two equations. One equation, two equation. 1 and 2. However, we have 3 unknowns. We might, let's say we know the mass of the card, simplicity. Okay. So we have 3 unknowns, which is R1, R2, and mu. So we can't solve it. So we need a third equation. To get the third equation, we are going to use the moments around this bottom point. Okay. Moments about point A. So around point A, so which force is attempting to rotate the card anti-clockwise? Moment anti-clockwise. Which force is trying to rotate the card anti-clockwise around the pivot? Mg. Do others people also understand why it is Mg? Some reaction, please. Look, we have a card like this, right? We fix it at this position. Imagine we are holding it at point A. So this is point A. So there are two forces that are trying to rotate the ruler. The mg force, this force, is pulling down. So it's trying to rotate it like this. It's trying to pull it that way. The reaction force is pushing that way. Do you see it the wrong way around? It's supposed to go from right to left, like this. Right, so we're holding it here. There's the weight, which is pulling that way. So it's trying to rotate it like this. It's trying to rotate it that way. And there's the reaction force, which pushing that way, who is trying to do that, undo the rotation. Does that make sense? Please react. If you're silent, I don't know what to think. Okay. Right, so the anti-clockwise moment, the moment that is the mg force, it's trying to rotate it that way. And this force is trying to rotate it that way. So the moment, the anti-clockwise moment is mg multiplied by the distance. Now with the distance is a bit, so this is the, if this is the card, This is half the length of the card, and we need this distance. This is the distance to the from the line. This is the pivot, and this is the line of force. So D is equal to L over 2 sine alpha. So L over 2 sine alpha, very similar to the previous one. We can say it's the component of mg perpendicular to the card, yes. In that case, we would say, so this is mg, this is mg. We have a component of mg perpendicular to the card, which is, and this is, which is mg sine alpha. And the moment would be L over 2 multiplied by mg sine alpha, which is the same result. I think thinking of it as the distance to the line of force is the same, is easier. And here we have the clockwise moment is R1 multiplied by the distance to the line of force, which is this one, D2. This is, so that's going to be L multiplied by cos alpha. And because it's in equilibrium, we know that the anticlockwise moment is equal to the clockwise moment. And that means mg L over 2 sine alpha equals R1L times cos alpha. So what can we cancel? L cancels. So R1 is equal to mg over 2 multiplied by tan alpha. All right, we found R1. That's useful. So R1 mg over 2 tan alpha equals mu multiplied by R2, and R2 is equal to mg, as you can see. Mg cancels, and mu is equal to tan alpha over 2. That's the answer. It does not contain the mass, as you can see. Mu tan alpha over 2. That's quite interesting, because if you remember, if you're on a slope, the minimum friction force, in order for you to remain stationary, do you remember what it is? To remain stationary on a slope. What is the friction force? It's tan alpha, friction coefficient. Has to be tan alpha. And here it's tan alpha over 2. So it's kind of consistent. It's a different situation, but I mean, yeah. Well, to remain stationary, it has to be greater or equal to tan alpha. But yeah. Right. Now the next two questions are kind of easier. They're less maths. So sorry, actually more maths probably, but less algebra. Okay. So this is a system to lift masses. So we turn the handle, and this bob pulls the rope up. So the rope ties around this large cylinder. At the same time, it unties from the small cylinder, so it goes down. But because the big cylinder is greater than the smaller cylinder, that means that the mass moves up. So if we rotate this anti-clockwise, right? Does everyone understand the setup? So water well. This is sort of like this, but a slightly more sophisticated. So this is a water well. So water well acts as a force multiplier. So why does it act as a force multiplier? Because the handle goes around a circle like this, but the rope goes around the circle like this. So this is your gear ratio, right? So because the handle goes around the big circle, around this circle, and that gives you a force multiplication. Okay, so you move the handle a long distance in order to move the bucket, right? And also it's convenient. It's just turning a handle. You don't have to pull the rope. It's a hassle. And if you let go, you can always catch the handle, and it's very difficult catching a rope, right? You get burns if you try to catch the ropes. I used to use one of those. I lived in a village where the only source of water was a well, so you get water, and then you use that water for whatever you want. Anyways, this is a more sophisticated system because it has two bobs. But no matter how complicated a system is, to find the mechanical advantage of it, you just need to find two things: how far you move and how far the thing that you are moving moves. Okay? So to find the mechanical advantage, find the mechanical advantage. How far do you move? How far well, in this case, does your hand move? And secondly, how far does the thing you are trying to move moves? Okay. Sorry for the handwriting. It's a bit pointless because you can't read what I've written. It's anyways. Okay, so for simplicity, let's take a single turn. In one complete turn of the handle, you move. So how far do you move? Does your hand move? In one turn of the handle. Yes, so can you give me a formula? In terms of you have L, you have R1, you have R2, you have M. So which one? Two pi L. Yeah, well done. You move 2 pi L because that's the radius of the circle of the handle. Right. So this is L. 2 pi L. Okay. Now, this bulb has circumference 2 pi R1. So this rope goes up by 2 pi R1. This rope, on the other hand, goes down by 2 pi R2. So left rope moves up 2 pi R1. Right rope moves down 2 pi R2. Okay. Now we need to work out how much does the mass M move. You would think that it is 2 pi R1 minus 2 pi R2. But I don't think it is. Look, imagine this rope, the right rope, was stationary. And this rope moves up by 1 meter. Moves up by 1 meter. How far does the central mass moves? It moves 0.5 meters. Moves 0.5 meters. Now, if this rope was stationary and this side of the rope moves down by 1 meter, the central thing would move down by 0.5 meters. So does everyone, do you understand why this is true? We've done pulleys, movable pulleys, and we went through that. So therefore, if one goes up, one goes down, you move half of that distance. So the mass moves up by, because it's a force multiplier, by 1/2 of 2 pi R1 minus 2 pi R2, which is pi R1 minus R2. Wow. Okay. And all we need to find is How can R1 and R2 be different if the rope is under constant tension and they're moving by those amounts? Oh, I don't see a contradiction. Like, look, let's do an experiment. Like doing. So you have a rope on this axis. So this is a small axle. All right. So this is a small axle, and then you have a big axle here. Okay. So you have two different axles, and you hang something from the bottom. Scissors. Never mind. Hang something from here. Now, if I rotate the top, I can definitely feel that my hand is going up. So because the big one winds and the small one unwinds. I'm winding the top one and I'm unwinding the bottom, the small one at the same time. Does that clear things up? I do an experiment. Try this. Zeno, does that clear things up in a way? Right. The thing is that the bottom of the rope, you need to understand that the bottom of the rope is not fixed. So it's not that I've tied something with a knot, right? I can't do this, for example, yeah? I can't do this. Because one rope goes down and the other rope goes up. But look, if one rope goes down, and the other one goes up, this rope becomes slack. That doesn't happen because the mass moves further along the rope. The mass is allowed to slide along the rope. So effectively, it's more like this. So if I move one up, the mass slides to a different position on the rope. So yeah, that's how it goes. All right, so and you end up with two numbers. This is how far you move, and this is how far the mass moves. And the mechanical advantage is equal to 2 pi L over pi R1 minus R2, which is pi cancels, 2L divided by R1 minus R2. And we got the numbers. R2 is 5 centimeters, R1 is 15, 2L is 40. So it's 2 times 40. 2 times 40 divided by 15 minus 5, which is 80 divided by 10, which is 8. So in order to lift 1000 newtons at constant speed, you need to apply a force of 1000 divided by 8, which is 125 newtons. Okay. And that works for any system. For any system, all you need to do is analyze how far you move and how far the system moves. That's it. That's quite cool, I think. Okay. All right. Now, I came up with this question like an hour ago. I just was thinking, what would be a good question? It's like, oh, I love it. I got inspired by the previous question. A typical wheel has a circumference of 2100 millimeters. By taking measurements from the picture, find the mechanical advantage of the bicycle. Okay. So what can we do here? Well, we need to answer two questions: how far you move and how far the system moves. Okay. So if the wheel has a circumference of 2100 millimeters, we can work out the radius. So the radius would be, everyone calculate the radius of the wheel. Three, 4. Okay. 300, let's stick with 330 millimeters. Now, find the radius of the big one. Let's call it R1. Oh. Yeah, let's call it R1. And this is the radius of the wheel, R1. Using measurements, use a ruler. Take a ruler and find the radius of that second of the big wheel. And then, because the pedals, this is R1. The pedals go around in a bigger circle. Find the radius let's call it L. This is L. Find L. Oh, sorry. Okay, I'll leave it like this and it won't move. Apologies, I didn't realize that. But you can use the link, right? So I'm going to take my ruler. And this is a 9. And this is 5. I'll write it down for me. So what is the radius of the green circle? I'm very sorry. Okay. I hope that's back. Not touching anything. That one is meters. R1. Come on, real life applied maths and physics. What is the, and then you need to find the radius of the back wheel, back thing. R1 is 82. Very good. That's a good estimate. Let's go with, let's stick with 80. Yeah. R1 is 80 millimeters. L, 165. It's double that. Yeah. Has anyone else got similar values? Does everyone understand how to do it? Right. So you just didn't have enough time to do it, or you're afraid to get it wrong. Okay. So what's R2? R2. R2. About 20. Yeah, 20 millimeters. I got 16, I think, but that's fine. Okay. And that's all we need. Okay. In one turn of the pedals, the pedal moves 2 pi L, moves 2 pi L. The small, the red, the chain, the chain moves 2 pi R1. Okay. Chain moves 2 pi R1. This causes the small cog, the back wheel to rotate. So it's going to be 2 pi R divided by 2 pi R2 times. Because if the chain moves to a distance of 2 pi R, and one rotation of the small cog is 2 pi R2, that means 2 pi R1 divided by 2 pi R2, that's the number of times the back wheel rotates. So the wheel travels 2100 millimeters multiplied by the number of times, 2 pi R1 times 2 pi R2. Okay, let's calculate. This goes 2 pi r1 over 2 pi r2. R1 is 80 millimeters, and this is 20. So 2 pi multiplied by 80 to 2 pi multiplied by 20. So that is 4 times. The wheel travels 4 multiplied by 2100 millimeters. So that is 8,400 millimeters. So the wheel travel, this is the distance travels, and we need to find in one turn of the pedal, that is 2 pi L, 2 times pi times L, which is 160. 2 pi, 2 times pi times 160, 1005, 1005 millimeters. All right, so the mechanical advantage is how much you move divided by how much the thing moves, which is roughly, okay, 1,000 divided by 8,000. 0.12.12. Okay. That means we lose out on force, but we win on speed. Okay. (0.12) for each if the pedal moves 1 meter, example, if pedals move 1 meter, the bicycle travels 8 meters, roughly, well, 8.4 meters, 8.4 meters. It's quite a significant win. So you move the pedals 1 meter and moves 8 meters. And then a person can apply 500 newtons to the pedals. What is the steepest hill the person can overcome? Well, we could talk about the torque produced by the pedals, then the torque produced by the chain, and then the torque produced at this chain, and then the torque produced at the wheel, and finally the force. But that's the thing. We've just found the force multiplier, and it's 0.12. So mechanical advantage, 500 units. What is the steepest hill the person can go? The mechanical advantage is 0.12. That means, so if the bicycle is on a steep hill, how much force do we need to keep it going? How much force needs to be applied to the bicycle in order for it to go up? How much force do we need to apply to a bicycle in order for it to go up? Well done. mg sine alpha. F has to be mg, because if you split mg into components, this is going to be mg cos alpha, and this is going to be mg sine alpha. So the force that you need to move up is going to be mg sine alpha. Mg sine alpha. The bicycle needs mg sine alpha to move up. But you have the mechanical advantage, which is your disadvantage because you need more force. The force on the pedals must be mg sine alpha divided by 0.12. Because you're winning speed, that means you're losing force. That means you need more force. But the maximum force that you can apply is 500 newtons. And so from here, okay, let's take a mass of the cyclist is 80 kilograms. So it's 80 times 10 times sine alpha divided by 0.12 equals 500. So sine alpha equals 500 times 0.12 divided by 800, which is times 500 divided by 800, 0.0748. So alpha is approximately 4.33 degrees. 4.3 degrees is the maximum incline the person can cycle up. So you see, from a question that's supposed to be quite difficult, we actually just, all we need is to find the mechanical advantage and then see, are we losing force? Are we winning force? And yeah, so that's it's an interesting. That's more like engineering if you like it, but it's fascinating nevertheless. Nevertheless, I mean, engineering is fascinating. It's just yeah. Right. So I think we'll finish here for today. I hope that was useful. And I'll see you next week for some maths. And yeah. Right. Welcome. See you everyone.